Okay. So today we're going to be talking about finite elements, and as Professor Tony Patterer, the professor who previously taught this part of the class, was saying, it's really about thinking in variational ways, or how he said it, think weakly. So the weak form is basically the finite element jargon of the variational form of a PDE. And so basically the first thing you have to get familiar with is how to convert a partial differential equation into a variational form. So that is something we started doing last Monday. So since it's a week past, and you guys are all working on finite volume project, so let me just go over with that again, just to make sure we are on the same page. Okay, so how do we convert a partial differential equation into weak form? So here I'll give two examples. One is the same as what we did last Monday, the Poisson equation, and two, I'm going to give another equation in structural mechanics, the Euler beam equation. So first of all, let's look at the Poisson equation, the second derivative of W with respect to just a single spatial dimension plus F would be equal to 0. And this is X in the domain of 0 and 1. You can easily generalize to other domains. And the boundary condition, right now we are just focusing on this very simple boundary condition. We are going to tell you a little bit later how to generalize to different kinds of boundary conditions. So now we have this particular type of differential equation coupled with boundary condition. Now let's turn it into a variational form. Okay, the reason we want to turn it into variational form is because finite element is essentially solving PDEs as an optimization problem. And computers cannot really solve optimization problems whose solution is a function in infinite dimensions. A function, you can change basically any point you want, right? Which means a function is an infinite dimensional object. Computers can solve finite dimensional problems. It can solve very large finite dimensional problems. Maybe you have hundreds of millions of dimensions you can tune, but like still, hundreds of millions is a finite number. So you need to make computers solve finite dimensional problems. Once you pose the equation as an optimization problem, then you can say, I'm going to restrict my solution into, for example, piecewise linear functions, right? We can split the domain into elements, and we can enforce the function to be a linear function within each element. So that's what finite element is doing. Convert the problem into a variational optimization problem and restrict the space into a certain class of functions we call a functional space, a finite dimensional functional space, and then solve that optimization under the restriction into that finite dimensional functional space. Okay, so the first task is really to turn the PDE into a variational optimization problem. So let's see, for example, how do we turn this equation into a variational optimization problem? Well, the first step is actually to figure out what is the variation, right? So the first step is actually to multiply the partial differential equation with a small variation. This small variation, let's write as delta W for now, right? So actually in most finite element literature, we actually use something different. For example, let's use V as a small infinitesimal variation of W. So let's say V is an infinitesimal variation of W. So V being infinitesimal variation means V has to satisfy, basically W plus V has to satisfy the same boundary condition, right? If W plus V has to satisfy the same boundary condition, that means V of 0 has to equal to V of 1 equal to 0. So that's a natural consequence of imposing V as a small variation of W. So then if we multiply this V with this function, with the residual of the differential equation, it has to be also 0, right? Because if the equation is satisfied, it is multiplied by any variation, it's still going to be 0. In particular, if I integrate it within the domain, it is still going to be 0, right? Actually, this is true for any V. for any small variation of v, this is going to be true. Okay, so now this allows me to start manipulating this integral form. We are going to manipulate this integral form into the variational form, or so-called the weak form. So really for this equation, the only step of manipulation is integration by parts, right? So basically integration by parts of the first term. Integration by parts is really removing, if I have the product of a function and the derivative of another function, integration by parts effectively pulls the derivative and put it on the other function. Here we have the v multiplied with the derivative of dw dx, right? The second order derivative is just simply the derivative of the first order derivative. So if we pull out a derivative, okay, of course we have a minus sign. We pull out the derivative in w. Here, the second derivative becomes the first derivative. And the derivative that is lost on w is going to be applied on v. So this is basically integration by parts. I mean, why is this the case? It's because if you add this term with that term, you form a complete derivative, right? So, okay, and we also have a boundary term that is a v times dw dx. So the function v and the function we pulled out from the derivative at 1 minus at 0. Okay, and we also have to add the term that we didn't change. This is equal to 0. Right, any questions on this step? Nope. Okay. The next step is actually to use this boundary condition of v, of the variation. This just means this whole term is actually 0, right? The boundary condition serves as a tool to remove the boundary terms from the integration by parts. And what we left with is minus integral of dv dx, or equivalently a small variation in dw dx times dw dx itself plus integral of vf is equal to 0. So here, let me highlight what we derived is actually the weak form of the Poisson's equation. So this is the weak form.